Hey there, hi there, ho there. Welcome back to section 3. Let's talk a little bit about plate tectonics. There's some differences between modern day and plate tectonics and what we saw 4 to 2.5 billion years ago. Remember, the processes are pretty much the same, but things that could be different, according to uniformitarianism, could be things like the rate of which it happens, which is what we see in the Archean. But let's dive into it, shall we? So some sort of plate tectonics took place in the Archean, and as I alluded to just a minute ago, but there was one big different a way that it differed from today's plate tectonics, and it was that plates moved much faster. All right, plates moved much faster. There was more residual heat left over from Earth's formation. There was more radiogenic heat, more radioactive material giving off their heat. Magma was generated more rapidly because of all of this heat. So everything was kind of in fast forward. More heat means mantle convection goes faster, means this whole process of plate tectonics goes faster. So that was the kind of the big difference. And when I mean faster, I don't mean like things were just moving around like this. Remember, now plates move, about the speed of the growth of your fingernails. So how fast did this occur in the Archean? I don't know, maybe 2-3 times that. So not like crazy fast, but faster due to there just being more heat around. So as a result of the kind of the rapid movement, continents obviously grew more rapidly as pieces kind of mushed together, as these new pieces of continental crust mushed together. That's a process called accretion. As island arcs come together with other island arcs and other parts of the crust. So that was happening faster, obviously. Also, because of this more heat and faster process, you get some ultramafic extrusive igneous rocks, which are rare, if not don't really happen nowadays. In fact, most ultramafic rocks are intrusive igneous rocks. We don't have any volcanic extrusive ultramafic igneous rocks. So because of this faster process and because of this heat, we do see extrusive ultramafic, very dark igneous rocks that usually date to pretty far back, and those are known as komatiites, and that's common from that era. So the origin of all of these cratons, so certainly there were several small little pieces of cratons that existed around the world during the Archean, and they grew and grew and grew along their margins via accretion, and they may have came together into larger units during the Proterozoic, which is what we're going to look at in Unit 8, but still, in the Precambrian. So all of these kind of craton formations are occurring in the Precambrian. But by the end of the Archean, which is about 2.5 billion years ago, 30 to 40% of the present volume of continental crust existed. So almost half of all the continental crusts existed by 2.5 billion years ago. The way crust evolved kind of around the world was probably similar to the evolution of the southern superior craton of Canada. Now, the North American craton, of which we have the exposed Canadian shield, it's actually made up of an amalgamation of a bunch of littler cratons to make up the larger one. And so the superior craton is just one of them. So this is the southern superior craton. It's right above Lake Superior, so it kind of borders U.S., dips into Minnesota a little bit, and then up into Canada. The darker green are greenstone belts. The lighter green are those granite gneiss complexes. And so what this shows us, it gives us a model for how cratons evolved via plate tectonics back in the Archean. So let's look at a cross section here, starting around this area. So let's look at a cross section. So imagine slicing, this part, the superior craton along this line, and then kind of tilting up and looking at it from the side to see what we well, what we see. So we'll first match up the rock units over here. So starting with the Uchi belt, and again that dark green is a greenstone belt. The light green, oops, let me move me a little bit. Let me move me up here for now. Okay. So this is what it kind of initially looked like, and then this is what it looked like after continued accretion, continued things kind of pushing against and kind of pushing up onto this area. This is before the Wawa belt. This is before the Wawa belt. This is after. So we have the Uchi. This is what it looked like before and then after. Oops. And then we have the English River granite gneiss complex before and then after. And then we have the Wobegon or Wabegon before and then after. And then we have the Quitico before and then after. And then, so this is all before. And then again, here comes another belt. Here comes another island arc. The Wawa greenstone belt and what it looks like as it pushed all the way through. So the evolution of this craton as these different island arcs of different early Precambrian rocks, granite gneiss complexes, and this thing's called greenstone belts, which we'll explore next section, kind of just amalgamated and came together and came together and came together to form this solid craton. All right, so can I put it back? So the deformation of this southern superior craton was part of a more extensive orogenic episode during the Archean. That's a kind of mountain building event, orogenic event. By the time this event ended, several other cratons in the area had formed that are also found in other parts of the Canadian Shield. So again, Canadian Shield and the North American, which is the exposed part of the North American craton, is actually composed of a bunch of smaller cratons that got kind of pushed together. This original continental crusty stuff that originally all kind of came together to form this larger North American craton. Okay. All right. I think that's about it. So let's go ahead and pause there. And when we come back, let's talk about these things that I'd mentioned a couple of times called greenstone belts. See you back here in just a second.